We went to the moon 6 times with computers weaker than a calculator. Then we stopped and forgot how to do it. That's not a joke. NASA literally cannot return to the moon as easily as they did in 1969, despite 50 years of technological progress. The reason why will make you question everything you believe about human advancement. And here is a question: if you could bring only one item to the moon to help you survive, what would it be? Comment down below. I'll pin the most creative answer. Now let's begin. The answer isn't simple. It's not just about money or politics, though those play huge roles. It's about something deeper, something that touches on how human ambition works, how technology evolves, and how the context of exploration changes over time. When Neil Armstrong took that famous first step on July 20th, 1969, it wasn't just a triumph of engineering, it was the culmination of an entire era, a moment when fear, competition, national pride, and unlimited resources converged to achieve the seemingly impossible. Let's start with the most obvious factor: money. The Apollo program cost approximately $25 billion in 1970s money. Adjusted for inflation, that's over $250 billion today. To put that in perspective, NASA's entire annual budget right now hovers around $25 billion. The Apollo program, at its peak, consumed more than 4% of the entire federal budget. Today, NASA gets about half of 1%. Imagine trying to rebuild the Golden Gate Bridge with a fraction of the original budget, and you'll start to understand the challenge. But it's not just about throwing money at the problem. During the Apollo era, the United States was locked in the Cold War with the Soviet Union. This wasn't merely a space race. It was an existential competition between two superpowers, each trying to prove their system of government, their way of life, was superior. When the Soviets launched Sputnik in 1957, Americans felt genuine fear. If the Soviets could put a satellite in orbit, they could put a nuclear weapon anywhere on Earth. Space became the ultimate high ground. President John F. Kennedy understood this perfectly. In his famous speech at Rice University in 1962, he didn't just say we were going to the moon because it was easy. He said we were doing it because it was hard, because that goal would serve to organize and measure the best of our energies and skills. The moon landing wasn't primarily about science or exploration. It was about demonstrating American technological supremacy to the entire world. That motivation, that driving force, simply doesn't exist today. Think about it this way. The Apollo program employed over 400,000 people at its peak. Engineers, scientists, technicians, manufacturers, all working toward a single goal with nearly unlimited government backing. Companies competed fiercely for contracts. Universities churned out aerospace engineers. The entire nation was mobilized. Children dreamed of becoming astronauts. It was a cultural phenomenon as much as a technological achievement. Today's space landscape looks completely different. We're not racing against a rival superpower. We're not trying to prove anything to the world in the same existential way. The motivation has shifted from geopolitical competition to scientific discovery, resource utilization, and long-term sustainability. These are worthwhile goals, absolutely, but they don't generate the same urgency or unlimited funding that the Cold War provided. Here's something fascinating that most people don't realize. We actually lost the ability to go to the moon. Not metaphorically, literally. The infrastructure that made Apollo possible no longer exists. The massive Saturn V rocket, the most powerful launch vehicle ever successfully flown, stopped production in 1970. The tooling, the specialized factories, the supply chains, all were dismantled. The engineers who designed these systems have mostly retired or passed away. Their knowledge, while documented, included countless informal tricks, techniques, and problem-solving approaches that never made it into the official manuals. This phenomenon has a name in engineering circles. It's called loss of organizational knowledge. Imagine trying to rebuild a medieval cathedral using only the original blueprints, without any of the master stonemasons who knew the secrets of their craft. That's somewhat analogous to our situation with Apollo-era technology. Yes, we have the designs, but recreating the manufacturing processes, re-establishing the supply chains, and rebuilding the institutional knowledge would be extraordinarily expensive and time-consuming. The Space Launch System, NASA's new heavy-lift rocket designed for the Artemis program, illustrates this perfectly. It's using some upgraded space shuttle components and new technology, but developing it has taken over a decade and cost more than $20 billion so far. Why? Because we're essentially relearning how to build super-heavy launch vehicles from scratch, incorporating modern safety standards, modern electronics, and modern materials science. Technology has advanced enormously since Apollo, but that creates its own challenges. Modern spacecraft are far more sophisticated, with capabilities the Apollo astronauts could only dream of. But sophistication means complexity, and complexity means more things that can go wrong. Apollo astronauts flew with relatively simple computers that had less processing power than a digital watch. They had limited life support, minimal scientific equipment, and stayed on the moon for at most 3 days. Today's plans are far more ambitious. NASA's Artemis program doesn't just want to plant flags and collect rocks. The goal is to establish sustainable human presence on the moon, to build habitats, to extract resources, to conduct long-term scientific research. We're talking about missions lasting weeks, or months, not days. We're planning to land near the lunar South Pole, where permanently shadowed craters might contain water ice, a crucial resource for future exploration. Water ice on the moon isn't just scientifically interesting. It's potentially revolutionary for space exploration. If we can access lunar water, we can split it into hydrogen and oxygen, creating rocket fuel right there on the moon. This would eliminate the need to carry all propellant from Earth, dramatically reducing the cost of missions to Mars and beyond. The moon could become a refueling station, a stepping stone to the rest of the solar system. But exploiting these resources requires technology and infrastructure far beyond what Apollo achieved. Landing near the South Pole also presents unique challenges. The Apollo missions landed near the lunar equator, where the sun is high in the sky for 2 weeks at a time, providing warmth and solar power. The polar regions experience different lighting conditions. Some areas receive nearly constant sunlight, perfect for solar panels, while nearby craters remain in perpetual darkness, colder than Pluto's surface. Navigating this extreme environment requires precision landing systems that didn't exist during Apollo. Another factor making return missions harder is our dramatically increased concern for safety. This might sound strange, but hear me out. The Apollo astronauts were test pilots, military men accustomed to extraordinary risk. They flew experimental aircraft that regularly crashed. They understood that space exploration was dangerous and accepted mortality rates that would be completely unacceptable today. Apollo 1 killed 3 astronauts during a ground test, and the program continued. Imagine the public reaction if that happened now. Modern space programs operate under entirely different safety standards. Every system has multiple redundancies. Every risk must be quantified, analyzed, and mitigated. Environmental reviews, safety assessments, and regulatory compliance add years to development timelines. This isn't bad. We should protect astronauts' lives, but it does make missions slower, more expensive, and more complex. Apollo succeeded partially because it moved fast and accepted risks that contemporary programs cannot. The political landscape has also shifted dramatically. Apollo had clear, bipartisan support for most of its existence. Yes, there were critics, but Congress generally funded NASA's requests because the moon landing was a national priority. Today, space exploration competes with countless other priorities, including healthcare, education, infrastructure, and defense. Political support fluctuates with each election cycle. Programs get started, delayed, redesigned, or cancelled as administrations change. The Constellation program, announced in 2004, aimed to return humans to the moon by 2020. It was cancelled in 2010. The Artemis program, announced in 2017, aims for a lunar landing in the mid-2020s, though that timeline keeps slipping. This stop-and-start approach wastes billions of dollars and years of effort. Engineers design systems that get cancelled before completion. Institutional knowledge gets lost as teams disband. Momentum evaporates. International collaboration, while beneficial in many ways, also adds complexity. The International Space Station demonstrates how countries can work together in space, sharing costs and expertise. The Artemis program includes partnerships with Canada, Europe, Japan, and other nations. This spreads the financial burden and brings diverse capabilities to the table. However, coordinating between different space agencies, each with their own procedures, timelines, and political pressures, requires enormous diplomatic effort and can slow progress. Private companies are changing the equation in fascinating ways. SpaceX, Blue Origin, and other commercial space firms are developing new launch vehicles and spacecraft with business models very different from traditional government contractors. SpaceX's Starship, currently in development, is designed to be fully reusable and capable of carrying over 100 tons to the lunar surface. If successful, it could dramatically reduce the cost of moon missions. But these vehicles are still being tested, and integrating commercial systems into NASA's programs presents its own challenges. Here's something that might surprise you. The radiation environment in space is actually more dangerous than we realized during Apollo. The astronauts were lucky. They spent only a few days traveling to and from the moon, and their missions happened during periods of relatively low solar activity. We now understand that cosmic rays and solar radiation pose serious long-term health risks, including cancer, cataracts, and neurological damage. For short Apollo-style missions, the risk was manageable. For extended stays on the moon, we need better shielding and protection. The Van Allen radiation belts, zones of energetic charged particles trapped by Earth's magnetic field, posed a particular challenge that Apollo had to navigate carefully. The spacecraft trajectory was designed to pass through the thinnest parts of these belts as quickly as possible, minimizing exposure. Modern missions will need to do the same, but with more sophisticated radiation monitoring and potentially better shielding, adding mass and complexity to spacecraft design. Solar particle events, sudden eruptions from the sun that send floods of dangerous radiation through space, were a constant threat during Apollo. The astronauts were simply lucky that no major events occurred while they were beyond Earth's protective magnetic field. For future long-duration missions, we'll need better space weather forecasting and radiation shelters on the lunar surface, where astronauts can take refuge during solar storms. The psychological challenges of space exploration are also better understood now. Apollo astronauts were away from Earth for 8 to 12 days maximum. Future lunar missions might last weeks or months. Extended isolation in a hostile environment takes a psychological toll. We've learned this from decades of operating the International Space Station and from analog missions in places like Antarctica. Crew selection, psychological support, and habitat design all need to account for mental health in ways that Apollo didn't. Communication delays, while minimal for the moon, still present challenges. It takes about 1.25 seconds for a radio signal to travel from Earth to the moon. That means a 2.5-second delay in conversation. Not terrible, but enough to make real-time remote operation of equipment difficult. During Apollo, astronauts had significant autonomy to make decisions. Modern missions might require more Earth-based control for safety and efficiency, but those communication delays mean astronauts still need extensive training and decision-making authority. The Moon itself presents hazards we didn't fully appreciate during Apollo. Lunar dust, for example, turned out to be far more troublesome than anyone expected. It's not like Earth dust. It's made of tiny, jagged glass shards created by billions of years of meteorite impacts. Without wind or water to smooth the particles, they remain razor-sharp. This dust gets into everything. It degraded spacesuits, clogged mechanisms, and caused equipment failures. Astronauts complained about its smell, described as similar to gunpowder, and experienced respiratory irritation. For short Apollo missions, lunar dust was an annoyance. For long-term presence, it's a serious engineering challenge. Dust mitigation systems, airlocks designed to minimize contamination, and materials resistant to abrasion all need to be developed. Some engineers are exploring technologies like electrostatic dust shields or special coatings. Others are designing habitats with sophisticated filtration systems. This is unglamorous work that doesn't make headlines, but it's absolutely essential for sustainable lunar exploration. The temperature extremes on the Moon are brutal. During the 2-week lunar day, surface temperatures can reach 250 degrees Fahrenheit. During the equally long lunar night, they plummet to -280 degrees. Apollo landed during lunar morning and left before the worst heat or cold arrived. For permanent bases, we need habitats that can withstand these temperature swings, power systems that work in darkness, and thermal control systems far more sophisticated than anything Apollo required. One approach being explored involves building habitats partially underground or covering them with lunar regolith, the layer of dust and broken rock covering the Moon's surface. Several feet of regolith provides excellent insulation against temperature extremes and radiation. Some scientists envision habitats inside lava tubes, natural tunnels formed by ancient volcanic activity. These would offer ready-made protection, but finding and accessing them presents its own challenges. Power generation for lunar bases is another complex issue. Apollo used fuel cells and batteries for its brief missions. Long-term habitation requires robust, reliable power sources. Solar panels work well during the lunar day, especially in polar regions that receive near-constant sunlight. But what about the 2-week polar night? Nuclear power is one solution. Small fission reactors could provide constant power regardless of sunlight. NASA and the Department of Energy are developing such systems, but they add complexity, mass, and regulatory hurdles. True utilization is key to making lunar exploration sustainable and affordable. Instead of bringing everything from Earth, future missions will manufacture what they need from local materials. This is called in situ resource utilization. Beyond extracting water for life support and fuel, scientists are exploring ways to produce oxygen from lunar regolith, to manufacture building materials using lunar soil, and to extract metals for construction and repairs. These technologies are still being developed and tested. Converting lunar regolith into useful materials requires high temperatures and specialized equipment. Extracting water from permanently shadowed craters means operating rovers and mining equipment in complete darkness at temperatures colder than liquid nitrogen. These are solvable problems, but they require investment, testing, and time. Apollo didn't worry about any of this because the missions were brief and self-contained. Launch windows and orbital mechanics add another layer of complexity. Apollo could launch whenever ready, within certain constraints. Modern missions need to coordinate with international partners, commercial launch providers, and often with robotic precursor missions. The Artemis program envisions a lunar gateway, a small space station in orbit around the Moon that serves as a staging point for surface missions. Building and maintaining this gateway requires numerous launches and complex orbital rendezvous operations. The gateway itself represents both an opportunity and a challenge. It provides a place to assemble lunar landers, to conduct research, and to serve as a safe haven. But it also adds cost and complexity that Apollo didn't have. Every additional component, every additional system, increases the chances of something going wrong and requires more time and money to develop and test. Here's where things get really interesting from a scientific perspective. We've learned an enormous amount about the Moon since Apollo. Robotic missions from NASA, Europe, China, India, and Japan have mapped the lunar surface in extraordinary detail, discovered water ice, detected unusual magnetic anomalies, and revealed a complex geological history. The Lunar Reconnaissance Orbiter, operating since 2009, has photographed the Moon at resolutions high enough to see the Apollo landing sites, including the tracks left by astronauts and rovers. This detailed knowledge is both helpful and daunting. We know exactly where we want to go and what resources might be available, but we also understand the challenges far better than the Apollo planners did. Ignorance can be liberating. The Apollo engineers solved problems as they arose, often with ingenious improvisation. Modern engineers must plan for contingencies decades in advance, designing systems to handle every conceivable scenario. China's Chang'e missions have demonstrated sophisticated robotic lunar exploration, including sample returns and the first ever landing on the Moon's far side. India's Chandrayaan missions have made important discoveries about lunar water and minerals. These international achievements show that lunar exploration is no longer an exclusive American or Soviet endeavor. Multiple nations now have the capability and ambition to explore the Moon, changing the competitive landscape entirely. This new space race, if we can call it that, lacks the existential urgency of the Cold War, but includes more players with diverse motivations. China has announced plans for crewed lunar missions in the coming decades. Russia, despite economic challenges, maintains lunar ambitions. India and Japan are developing advanced capabilities. The United States is no longer the sole superpower in space, which means cooperation becomes more important even as competition continues. Commercial interest in the Moon is also growing. Companies see potential profits in lunar tourism, resource extraction, and providing services to government space agencies. Some envision mining helium-3, a rare isotope that could theoretically fuel fusion reactors, though that technology remains decades away if it's possible at all. Others plan to establish commercial research facilities or even hotels. Whether these business models will prove viable remains uncertain, but they represent new motivations for lunar exploration beyond government science programs. Legal and regulatory frameworks for space activities have evolved considerably since Apollo. The Outer Space Treaty of 1967, signed during the Apollo era, establishes that nations cannot claim sovereignty over celestial bodies. The Moon belongs to all humanity. But what does that mean for resource extraction? Can companies mine lunar water or minerals? Can nations establish exclusive zones around their bases? These questions are being debated right now in international forums, and the lack of clear answers creates uncertainty that complicates planning. If you crave answers to questions like this, make sure to subscribe and give this video a like. The universe isn't done surprising you, and neither are we. The Artemis Accords, introduced in 2020, attempt to establish principles for peaceful lunar exploration, including transparency, interoperability, and commitments to preserve historic sites like the Apollo landing locations. Multiple countries have signed these accords, but not everyone agrees with the framework. China and Russia, for example, have not signed and are developing their own partnership for lunar exploration. This fragmentation of international space governance adds another layer of complexity to modern lunar missions. Environmental protection is now a consideration that didn't exist during Apollo. Scientists worry about contaminating the moon with Earth microbes or about disturbing scientifically valuable sites. The permanently shadowed craters that might contain ancient water ice are particularly sensitive. If we contaminate them before studying them properly, we might lose irreplaceable scientific data about the early solar system. Balancing exploration with preservation requires careful planning and adds constraints that Apollo never faced. There's also the question of what we're actually trying to accomplish. Apollo's goal was clear and simple: land humans on the moon and return them safely to demonstrate American capability. Mission accomplished. Today's objectives are murkier. Are we preparing for Mars missions, establishing permanent lunar presence, conducting science, exploiting resources, building international partnerships, all of the above? This lack of singular focus can be healthy, allowing for diverse objectives, but it also makes programs harder to plan, fund, and justify to the public. Public engagement with space exploration has changed dramatically. During Apollo, hundreds of millions of people worldwide watched the moon landings on television. It was the biggest media event in history. Today, we're saturated with spectacular images from space. Mars rovers send back high-definition photos daily. Telescopes reveal distant galaxies in breathtaking detail. The International Space Station provides a constant human presence in orbit. The moon landing, if it happened tomorrow, would certainly be news, but would it captivate the world the way Apollo did? This cultural shift affects political support and funding. Politicians respond to public enthusiasm. If voters care passionately about space exploration, representatives will fund it. But space competes with immediate concerns like economic security, healthcare, climate change, and countless other issues. Making the case for spending billions on lunar missions requires demonstrating clear benefits, whether scientific discoveries, technological spin-offs, economic opportunities, or inspirational value. The technological spin-offs from Apollo were substantial: integrated circuits, cordless tools, freeze-dried food, water purification systems, and many other technologies benefited from space program investment. Modern lunar programs promise similar benefits. Advances in robotics, artificial intelligence, materials science, life support systems, and renewable energy driven by space exploration have applications on Earth. But these benefits are often indirect and take years to materialize, making them harder to use as justification for immediate spending. Education and inspiration remain powerful arguments for space exploration. The Apollo program inspired an entire generation to pursue careers in science and engineering. Those individuals went on to create innovations that transformed our world. Can Artemis do the same? In an era where young people face climate anxiety, economic uncertainty, and political polarization, does lunar exploration offer the hopeful vision of the future that we desperately need? Many space advocates argue yes, that reaching beyond our planet reminds us of our shared humanity and our capacity to achieve extraordinary things when we work together. Let's talk about the actual hardware being developed for lunar return. NASA's Space Launch System is the most powerful rocket currently in development, designed to launch the Orion crew capsule toward the Moon. The first uncrewed test flight, Artemis 1, successfully orbited the Moon in late 2022 after years of delays. Artemis 2 will carry astronauts around the Moon without landing, currently planned for 2025. Artemis 3 aims to land humans near the South Pole, potentially in 2026 or later. The Orion spacecraft represents a significant advance over the Apollo command module. It has modern computers, life support systems, and radiation shielding. It can support crews for up to 21 days, far longer than Apollo's capabilities. The European Space Agency provides the service module, which supplies propulsion, power, and life support, demonstrating international collaboration. But developing and testing Orion has taken nearly 2 decades and cost over $20 billion, illustrating how much more expensive and time-consuming modern spacecraft development has become. The lunar lander for Artemis is being developed by SpaceX using a version of their Starship vehicle. This is a radical departure from Apollo's approach. The lunar module was purpose-built for moon landings, relatively small, and launched directly from Earth as part of the Saturn V stack. Starship is a massive vehicle designed for multiple purposes, including Mars missions and point-to-point Earth transport. Using it as a lunar lander requires orbital refueling, a technology that has never been done on the scale required. Multiple tanker starships will need to launch and transfer propellant to the lunar Starship in Earth orbit before it heads to the Moon. This orbital refueling architecture is innovative and potentially cost-effective in the long run, but it's also complex and unproven. Each refueling operation is a critical event that must succeed for the mission to proceed. The reliability of this approach depends on SpaceX successfully developing rapid, routine Starship launches, something they're working toward but haven't yet achieved. The dependence on a single commercial provider for such a critical capability also raises questions about redundancy and risk management. SpaceX's approach to development differs dramatically from traditional aerospace contractors. They build prototypes, test them to failure, learn from explosions, and iterate rapidly. This philosophy has produced remarkable successes, including the Falcon 9, the first orbital-class reusable rocket, and the Dragon capsule that carries astronauts to the International Space Station. But it also involves spectacular failures along the way. Several early Starship prototypes exploded during testing. This rapid iteration approach works well for privately funded development, but integrating it into NASA's risk-averse culture creates tension. The contrast between SpaceX's methods and NASA's traditional approaches highlights a fundamental shift in how space exploration is conducted. Apollo was entirely government-run. NASA designed the systems, hired contractors to build them according to strict specifications, and controlled every aspect of operations. Today's model increasingly relies on commercial partners who own and operate their own systems, with NASA as a customer rather than the primary developer. This can be more efficient and innovative, but it also means less direct control. Other companies are developing lunar infrastructure as well. Blue Origin, founded by Amazon's Jeff Bezos, is working on the Blue Moon lander. Various firms are building lunar rovers, communications satellites, and resource extraction equipment. This emerging lunar economy could eventually make moon missions routine and affordable, but we're still in the early stages. Most of these systems are years from operational use, and many will face setbacks, delays, and potentially failures before they succeed. Testing and validation present enormous challenges. During Apollo, NASA could test components and systems on Earth, but the actual lunar environment could only be simulated imperfectly. The same is true today, but our standards for testing are much more rigorous. Every system must be tested extensively, often for years, before it's approved for human missions. Finding ways to test lunar equipment on Earth, from dust mitigation systems to radiation shielding, requires creative approaches and specialized facilities. Some testing happens in lunar analogs, places on Earth that resemble the Moon in certain ways. Volcanic fields in Iceland, Arizona, and Hawaii provide rocky terrain similar to Lunar Maria. Antarctic bases offer isolation, harsh conditions, and psychological challenges similar to lunar habitats. Desert research stations allow testing of rovers and spacesuits, but none of these perfectly replicate the 1/6 gravity, vacuum, radiation, and temperature extremes of the actual moon. Some things can only be truly tested in the lunar environment itself. This is where robotic precursor missions become essential. Before landing humans at the lunar South Pole, NASA and its partners are sending robots to scout locations, test technologies, and reduce risks. The Commercial Lunar Payload Services Program contracts with private companies to deliver scientific instruments and technology demonstrations to the moon. These missions are smaller and less expensive than Apollo-era probes, taking advantage of modern miniaturization and commercial launch capabilities. Several of these robotic landers have already launched or are in development. Some have succeeded, others have failed. In 2019, Israel's Bereshit lander crashed during its landing attempt. India's Vikram lander also crashed that same year, though India succeeded with Chandrayaan-3 in 2023. Japan's Slim lander achieved a precision landing in 2024, but ended up in an awkward position. These missions, both successes and failures, provide valuable data and experience that inform future attempts. The moon's environment is utterly unforgiving of mistakes. There's no atmosphere to slow descent, so landing requires precise rocket burns. There's no GPS for navigation, so landers must use cameras and sensors to identify safe landing spots autonomously. Communication delays mean that critical landing maneuvers happen too quickly for Earth-based controllers to intervene. Everything must work perfectly, or the mission fails. Apollo succeeded 6 times in a row, but we also remember Apollo 13, which barely made it home after an oxygen tank explosion. Modern missions aim for even higher reliability, but perfection is impossible in such a challenging environment. The question becomes how to build systems robust enough to handle failures gracefully. Redundancy helps, having backup systems for critical functions. Autonomy matters, giving spacecraft the intelligence to recognize and respond to problems without human intervention. Simplicity is valuable. Fewer components mean fewer potential failures. But these principles often conflict with each other and with cost constraints. Let's consider the human factors more deeply. Astronaut training for lunar missions is far more extensive than for low Earth orbit operations. International Space Station crews train for about 2 years before their missions. Lunar astronauts will need similar or longer preparation, learning not just how to operate their spacecraft, but also how to work in 1/6 gravity, how to conduct geological fieldwork, how to maintain equipment in the harsh lunar environment, and how to respond to emergencies when Earth is days away rather than hours. The Artemis program has committed to landing the first woman and the first person of color on the moon, reflecting how our values around representation and inclusion have evolved since Apollo. The original Mercury 7 astronauts were all white military test pilots. Women and minorities were systematically excluded. Today's astronaut corps is far more diverse, drawing from broader backgrounds including scientists, engineers, physicians, and international partners. This diversity strengthens the program, bringing different perspectives and skills to exploration. Selecting landing sites for Artemis involves balancing multiple competing factors. Scientific interest points towards certain regions with unique geology or potential resources. Engineering constraints favor flatter, less rocky terrain. Lighting conditions affect solar power availability and thermal management. Communication with Earth requires certain geometries. Access to permanently shadowed craters might be scientifically valuable, but operationally challenging. No site is perfect, so mission planners must carefully weigh trade-offs. The South Pole region, currently favored for Artemis 3, offers several advantages. Some crater rims receive nearly continuous sunlight, providing constant solar power and moderate temperatures. Nearby permanently shadowed craters likely contain water ice. The terrain is scientifically interesting, potentially revealing information about the Moon's history and the early solar system. But landing there is harder than Apollo's equatorial sites. The Sun sits low on the horizon, creating long shadows and difficult lighting conditions for navigation. The terrain is rough and mountainous. Precision landing technology is crucial for these challenging sites. Apollo landing accuracy was measured in kilometers. The astronauts could see the terrain and manually pilot their lander to safe spots, but they had limited fuel for this maneuvering. Artemis landers will use advanced sensors, including LiDAR cameras and terrain-matching algorithms, to identify hazards like boulders and slopes, then automatically navigate to safe landing zones with accuracy measured in meters. This technology is being tested on robotic missions before trusting it with human crews. Once on the surface, astronauts will conduct far more extensive activities than Apollo crews managed. Instead of 2 or 3 brief excursions totaling a few hours, Artemis missions plan for multiple extended sorties over a week or more. Modern spacesuits currently in development will be more flexible, more comfortable, and more capable than the Apollo suits. They'll provide better mobility, longer life support duration, and integrated communication systems. But developing these advanced suits has proven challenging and expensive, with multiple redesigns and contract changes. Mobility on the lunar surface matters enormously. Apollo astronauts walked or used the Lunar roving vehicle, a battery-powered car that allowed them to travel several kilometers from the landing site. Future missions will have more capable rovers, potentially pressurized vehicles where astronauts can work without spacesuits. Some concepts envision habitats on wheels that can relocate to different sites, combining mobility with living space. These systems are still conceptual, but they represent the ambition driving current planning. Scientific instruments for lunar missions have advanced tremendously. Apollo astronauts deployed seismometers, reflectors for laser ranging, and other experiments that operated for years. They collected 842 pounds of lunar rocks and soil, samples that scientists still study today. Modern missions will deploy more sophisticated sensors, drill deeper cores, conduct more detailed chemical analyses, and potentially establish permanent observatories for astronomy, fundamental physics, and planetary science. The Moon offers unique advantages for certain types of research. Radio telescopes on the far side, permanently shielded from Earth's radio noise, could observe the universe at wavelengths impossible to study from Earth. Gravitational wave detectors on the Moon might achieve sensitivities beyond Earth-based instruments. Particle physics experiments could search for dark matter or test fundamental theories. The stable, airless environment allows long-term observations impossible anywhere on Earth. These scientific opportunities justify lunar exploration beyond just preparing for Mars. Speaking of Mars, many people view the Moon as a training ground for eventual red planet missions. The logic makes sense. Mars is orders of magnitude harder to reach than the Moon. The journey takes 6 to 9 months each way. Crews would spend 2 years away from Earth, isolated in ways no humans have ever experienced. Before attempting Mars, shouldn't we practice on the Moon, just a few days from home? Develop technologies, procedures, and experience in a challenging but relatively accessible environment. This argument has merit, but it's not universally accepted. Some Mars advocates argue that the Moon and Mars are different enough that lunar experience doesn't directly translate. The Moon has no atmosphere, Mars has a thin one. Mars has abundant carbon dioxide, the Moon doesn't. The gravity is different, 1/6 on the Moon versus 3/8 on Mars. Resources, terrain, communication delays, everything differs. Spending decades and hundreds of billions on the Moon might delay Mars missions rather than enable them. Others counter that the relevant experience isn't about specific environments, but about building and operating infrastructure in hostile places far from Earth. Learning to manufacture propellant from local resources, to grow food in controlled environments, to maintain complex systems with limited supplies, to handle medical emergencies without evacuation options. All these skills apply whether you're on the Moon or Mars. The Moon lets you develop and prove these capabilities with a margin for error that Mars won't allow. The sustainability question looms large. Apollo was a sprint, an intensive effort to achieve a goal then move on. Artemis aims for a marathon, establishing enduring presence that builds capability over time. This requires fundamentally different approaches. Instead of custom building everything for specific missions, we need modular, reusable systems. Instead of throwing away hardware, we need to maintain and repair it. Instead of depending entirely on Earth for supplies, we need to live off the land as much as possible. Economic sustainability matters too. Government funding fluctuates with political winds. For lunar exploration to endure long-term, it probably needs economic justifications beyond science and inspiration. What can the Moon provide that's valuable enough to sustain commercial interest? Tourism is one possibility, though the market size remains uncertain and the costs are currently astronomical. Resource extraction, particularly water for propellant, might create genuine business opportunities if launch costs continue declining and space activity increases. Some visionaries imagine the Moon as a manufacturing center, using lunar materials and solar energy to build structures for use in space. Without atmospheric drag or gravity wells, the Moon could efficiently launch components for large space stations, solar power satellites, or spacecraft headed to Mars. The low gravity makes launching from the Moon easier than from Earth, and the abundant solar energy and raw materials could support industrial processes. But we're decades away from such capabilities. If they prove viable at all, the infrastructure required for sustained lunar presence is staggering. Habitats with reliable life support for months or years. Power systems that work through 2-week lunar nights. Communication networks providing constant contact with Earth and between lunar sites. Landing pads to prevent rockets from sandblasting everything with high-velocity dust. Roads or trails connecting different facilities. Storage for propellant, consumables and spare parts. Medical facilities for treating injuries and illnesses. The list goes on and on. Each piece of infrastructure requires launches from Earth, at least initially. Even with reusable rockets dramatically reducing costs, transporting hundreds of tons of equipment to the Moon represents a massive logistical undertaking. Careful planning is essential to prioritize what goes up first, how systems integrate, and how to maintain progress if some launches fail or get delayed. Apollo didn't worry about infrastructure because missions were self-contained. Artemis must think decades ahead. Construction on the Moon presents unique challenges. Robotic systems will likely do most of the work, assembling habitats, deploying solar panels, and excavating protective berms. But designing robots that function reliably in lunar dust, vacuum, temperature extremes, and radiation is extraordinarily difficult. Teleoperation from Earth has that frustrating 2.5-second delay. Full autonomy requires artificial intelligence sophisticated enough to handle unexpected situations. We're making progress on these technologies, but they're not ready yet. Some concepts involve 3-dimensional printing structures using lunar regolith as raw material. Microwave or solar sintering could melt the regolith into solid forms, creating walls, landing pads, or radiation shielding without transporting building materials from Earth. The European Space Agency and others have tested these concepts in laboratories, producing bricks and structures from simulated lunar soil, But scaling up to actual lunar construction requires equipment that can function autonomously for extended periods in the harsh lunar environment. Food production is another frontier. Apollo carried all food from Earth, freeze-dried meals that astronauts rehydrated and ate. For long-duration missions, growing fresh food becomes important for nutrition, variety, and psychological well-being. The International Space Station has successfully grown lettuce, radishes, and other crops in microgravity. The Moon's 1/6 gravity is different, neither Earth normal nor weightlessness. We're not entirely sure how plants will grow, though experiments are planned. Lunar greenhouses would need artificial lighting, controlled atmosphere, water recycling, and protection from radiation and temperature extremes. The energy requirements are substantial. Whether it's more efficient to grow food on the Moon or import it from Earth depends on many factors, including how many people are living there, how long they stay, and what transportation costs look like. Early missions will certainly bring food from Earth, but long-term bases might eventually produce at least some of their own. Medical care in lunar environments poses serious challenges. Minor injuries that would be routine on Earth become complicated when you're wearing a spacesuit or in a habitat days away from advanced medical facilities. A broken bone, a severe infection, a cardiac emergency, these could be life-threatening without proper treatment. Lunar missions will include medical officers with extensive training, telemedicine capabilities for consulting with Earth-based specialists, and equipment for handling likely emergencies. But there are limits to what can be done remotely. Surgical intervention in 1/6 gravity has never been attempted. Blood, fluids, and debris would behave differently than in Earth gravity or the microgravity of orbit. Anesthesia, wound healing, and recovery all might present unexpected complications. Medical researchers are thinking through these scenarios, developing protocols and equipment, but until we actually establish lunar bases, much remains theoretical. This uncertainty is another factor making lunar return harder than the first missions, which simply had to keep astronauts healthy for a few days. Psychological support becomes crucial for extended missions. The Apollo astronauts were busy constantly during their brief stays, with little time for boredom or homesickness. Longer missions mean crews will experience the same psychological stresses as Antarctic researchers or submarine crews. Isolation, confinement, monotony, interpersonal tensions, and the inability to simply go outside or leave if problems arise. Careful crew selection, psychological training, communication with family, recreational activities, and habitat design all help, but maintaining mental health in such extreme environments requires ongoing attention. The view from the Moon offers both comfort and alienation. Earth hangs in the black sky, a beautiful blue marble reminding astronauts of home, but it's 250,000 miles away, impossibly distant. The Apollo astronauts reported profound emotional responses to seeing Earth from the Moon, a perspective shift that many described as life-changing. How will this Earthrise effect impact crews spending weeks or months on the lunar surface? Will it inspire and motivate them, or emphasize their isolation? Probably both, in ways we can't fully predict until humans actually experience it. Let's return to the technical challenges. Navigation on the Moon lacks the conveniences we take for granted on Earth. No GPS constellation provides positioning information. No magnetic field allows compass navigation. The Sun moves slowly across the sky, taking about 27 Earth days to complete a circuit. Stars are always visible in the black sky, useful for navigation but requiring equipment and knowledge to use effectively. Future lunar infrastructure will likely include positioning satellites and surface beacons, but early missions must navigate using cameras, inertial measurement units, and careful tracking of their movements. Communication infrastructure is being developed to support sustained lunar operations. NASA's Lunar Communications Relay and Navigation Systems program aims to establish satellites around the Moon, providing constant communication coverage and positioning services, similar to GPS but for the Moon. This infrastructure doesn't exist yet. Apollo missions communicated directly with Earth when the spacecraft had line of sight, which meant no communication during portions of each orbit when they were behind the Moon. For permanent bases, constant communication is essential. Data transmission rates have improved enormously since Apollo. The entire Apollo program transmitted less data than a single modern smartphone photo. Today's missions generate terabytes of high-resolution images, sensor data, and video. Transmitting this information across 250,000 miles requires powerful transmitters, large antennas, and sophisticated signal processing. NASA's Deep Space Network, a collection of large radio antennas around Earth, handles communication with distant spacecraft, but demand exceeds capacity. New antennas and systems are being built, but they're expensive and take years to construct. Cybersecurity is an emerging concern that Apollo never faced. Modern spacecraft and ground systems are essentially networks of computers communicating across vast distances. Protecting these systems from hacking, interference, or sabotage requires sophisticated security measures. An adversary who could commandeer a lunar lander or corrupt life support systems could endanger astronauts' lives. As space becomes more contested and commercialized, cybersecurity becomes as important as physical safety systems. The global space economy is transforming rapidly. When Apollo flew, space activities were almost exclusively governmental. Today, commercial space generates over $400 billion annually in revenue, mostly from satellites providing communications, navigation, Earth observation, and other services. This commercial ecosystem makes certain aspects of lunar exploration easier and cheaper. Launching payloads costs a fraction of what it did in the Apollo era, thanks to commercial competition and reusable rockets. However, this commercialization also creates complications. Companies prioritize profit and shareholder value, not necessarily scientific discovery or exploration for its own sake. Business models might not align with NASA's goals or timelines. Companies go bankrupt, get acquired, or pivot to different markets. Depending on commercial partners for critical mission elements introduces uncertainties that government-run programs don't face. Balancing these relationships requires careful contract structures, oversight, and contingency planning. International law and space governance continue evolving. Questions about property rights, resource extraction, environmental protection, and military activities in space remain contentious. The Artemis Accords attempt to establish norms for peaceful lunar exploration, but they're not binding treaties, and not all spacefaring nations have signed them. China and Russia are developing their own partnership, the International Lunar Research Station, with different principles and participants. This bifurcation could lead to competing lunar infrastructure and potentially conflicting claims or operations. Some worry about a new space race creating tensions rather than cooperation. If multiple nations establish bases in close proximity, particularly near valuable resources like water ice deposits, conflicts could arise over access, boundaries, or environmental impacts. Who decides where one nation's operations end and another's begin? What happens if mining activities contaminate scientifically valuable sites? These aren't immediate concerns, but they'll become pressing issues as lunar activity intensifies. Others see competition as healthy, driving innovation and progress as it did during the Apollo era. The prospect of China landing astronauts on the Moon might motivate increased American investment, just as Sputnik did in the 1950s. Multiple nations and companies pursuing lunar goals through different approaches increases the chances that some will succeed, advancing humanity's capabilities regardless of who gets there first. Competition and cooperation aren't mutually exclusive. They can coexist productively. The environmental impact of space activities deserves consideration. Rocket launches release pollutants into Earth's atmosphere. Space debris from satellites and rocket stages clutters Earth orbit. What about the Moon's environment? Should we treat it as an untouched wilderness to be preserved, or as a resource to be utilized? The Moon has no ecosystem to damage, no life to protect that we know of. But it does have scientific value as a record of solar system history and irreplaceable historic sites from past missions. Some scientists argue for lunar parks or preserves, protected areas where human activity is restricted to preserve scientific or historical value. The Apollo landing sites, for instance, contain artifacts and footprints that tell the story of humanity's first steps on another world. Should these be protected like archaeological sites on Earth? The Outer Space Treaty requires avoiding harmful contamination, but doesn't specify what that means for airless bodies like the Moon. International agreement on these principles would help, but achieving consensus is challenging. Climate change on Earth adds urgency and complexity to space exploration discussions. Some argue we should focus resources on fixing our planet's problems rather than spending billions exploring space. Others counter that space technologies, from satellite monitoring to solar power research, contribute directly to addressing climate change. The perspective and inspiration gained from space exploration might help humanity appreciate Earth's fragility and unite around protecting it. These arguments will continue shaping public support and political decisions about lunar programs. The technology developed for lunar exploration often has terrestrial applications. Life support systems designed for space can help in disaster relief or remote locations on Earth. Robotic technologies developed for lunar construction could assist in dangerous environments like nuclear facilities or deep-sea operations. Materials science advances for spacecraft could improve everything from electronics to transportation. Medical technologies for monitoring astronaut health could benefit patients on Earth. These spillover benefits are real, though sometimes hard to quantify or predict. Education and workforce development represent crucial but often overlooked challenges. The Apollo program could draw on engineers and scientists trained during World War II and the immediate post-war period. Today's programs need specialists in fields that barely existed during Apollo, from artificial intelligence to advanced materials science. Universities must train the workforce, but enrollment in science and engineering fields fluctuates with job market perceptions and cultural factors. Sustaining decades-long programs requires a pipeline of talent that takes years to develop. Diversity in the workforce matters not just for fairness, but for capability. Different perspectives lead to better problem-solving and innovation. The Apollo workforce was predominantly white and male, reflecting the broader society's discrimination. Today's space industry is more diverse but still has work to do. Encouraging young people from all backgrounds to pursue space-related careers strengthens the field and ensures the best minds contribute regardless of their demographic characteristics. Public outreach and science communication play vital roles in maintaining support for space exploration. During Apollo, everyone watched on television because there were few channels and space was genuinely novel. Today's media landscape is fragmented into countless channels, platforms, and interests. Reaching people requires sophisticated communication strategies across multiple platforms. NASA and other space agencies have become adept at social media, streaming, and immersive content, but capturing sustained public attention remains challenging. the storytelling around space exploration has evolved. Apollo offered a simple, compelling narrative of heroes venturing into the unknown, representing their nation and all humanity. Modern missions involve international partnerships, commercial contractors, robotic precursors, and incremental progress over years or decades. The story is more complex, harder to distill into sound bites or dramatic moments. Finding ways to make this complexity engaging and inspiring challenges communicators, but is essential for maintaining public enthusiasm. Virtual and augmented reality technologies offer new possibilities for bringing space exploration to people. Imagine experiencing a lunar landing through a VR headset, seeing what the astronauts see, feeling immersed in the environment. Or using augmented reality to visualize lunar habitats in your living room, understanding their scale and design. These technologies can make space exploration tangible and exciting for people who will never actually go to space, building support and inspiring the next generation. The economics of space exploration merit deeper examination. Apollo cost roughly $280 billion in today's money, spread over about a decade. That's enormous, but it represented less than 3% of the federal budget at its peak. Today's space exploration budgets are smaller in both absolute terms and as a percentage of government spending. NASA's entire budget is about $25 billion annually, with only a fraction dedicated to lunar programs. Achieving ambitious goals with limited resources requires efficient approaches and sustained commitment. Cost overruns and schedule delays plague aerospace programs, not just space exploration. The James Webb Space Telescope, originally budgeted at $500 million and planned for launch in 2007, eventually cost $10 billion and launched in 2021. The Space Launch System has experienced similar overruns. These problems stem from the difficulty of developing unprecedented technologies, changing requirements, political pressures, and organizational challenges. Critics argue for better management. Defenders note that pushing technological boundaries inevitably encounters unexpected difficulties. Fixed-price contracts, where companies agree to deliver capabilities for a set price rather than being reimbursed for costs plus profit, can help control expenses. SpaceX's development of the Falcon 9 and Dragon spacecraft under fixed-price contracts cost NASA far less than traditional cost-plus arrangements might have. However, fixed-price contracts work best when requirements are clear and technologies relatively mature. For cutting-edge development with many unknowns, they can lead companies to underbid, then struggle to deliver, or to cut corners that compromise safety or capability. The opportunity cost of space exploration deserves honest discussion. Every dollar spent on lunar missions is a dollar not spent on other priorities, whether healthcare, education, infrastructure, or deficit reduction. Space advocates must make the case that exploration provides sufficient return on investment, whether through scientific knowledge, technological advancement, economic opportunities, or intangible benefits like inspiration and international cooperation. These arguments resonate differently with different audiences, and there's no objectively correct answer about how society should allocate resources. Philosophically, space exploration connects to deep questions about humanity's purpose and future. Are we meant to remain on one planet forever, or to become a multi-planetary species spreading through the cosmos? Does our long-term survival require backing up civilization on other worlds, protecting against existential risks like asteroid impacts, supervolcanoes, or nuclear war? Or should we focus on stewarding Earth, the only home we know supports life? These questions don't have simple answers, but they frame debates about whether and why we should explore space. If you are still watching, please subscribe and give this video a like. Your support means a lot to me. Join us as we explore the strangest truths of the universe. The moon represents a small step in cosmic terms, but a giant leap for our species. It's the farthest humans have traveled from Earth, a 250,000-mile journey into a genuinely alien environment. Returning and establishing presence there would demonstrate capability, build confidence, and develop technologies for venturing further. Whether humanity's future lies in space or Earth, the knowledge and perspective gained from lunar exploration enriches our understanding of ourselves, our planet, and our universe. Some philosophers argue that exploration is fundamentally human, that curiosity and the drive to discover new frontiers are essential to who we are. Throughout history, humans have explored mountains, oceans, poles, and continents, often at great cost and risk. Space is simply the next frontier, and turning away from it would represent a failure of imagination and ambition. Others counter that past exploration often involved colonialism, exploitation, and suffering, patterns we should avoid repeating rather than extend into space. These ethical considerations matter increasingly as space activities expand. How do we ensure that lunar exploration benefits all humanity, not just wealthy nations or corporations? How do we protect scientific and historic sites while enabling economic development? How do we avoid creating the same inequalities and conflicts in space that plague Earth? Wrestling with these questions now, before large-scale lunar activities commence, might help us establish better frameworks than addressing problems after they arise. The timeline for returning to the moon keeps slipping, and this frustrates space enthusiasts. Artemis 3 was originally planned for 2024, then pushed to 2025, now targeting 2026 or potentially later. These delays reflect real challenges in developing complex systems, but they also erode confidence and support. Each delay costs money and momentum. Political leaders lose patience, public interest wanes. Finding ways to maintain steady progress despite inevitable setbacks is crucial for program success. Some suggest that NASA should embrace a more iterative approach, launching missions as systems become ready rather than waiting until everything is perfect. Apollo essentially did this, flying missions of increasing complexity and risk, learning at each step. The commercial space industry follows this model, testing early and often, accepting failures as learning opportunities. NASA's culture has become more risk-averse over decades, understandably after the Challenger and Columbia tragedies killed 14 astronauts. Balancing safety with progress is an ongoing challenge. Looking at the bigger picture, humanity stands at an interesting moment. We have the technology to return to the moon and establish sustained presence. We have robots exploring Mars and probes visiting asteroids and the outer solar system. We're discovering thousands of planets around other stars and detecting gravitational waves from colliding black holes. Our understanding of the universe has expanded exponentially since Apollo. Yet we've also spent the last half-century in low Earth orbit, circling a few hundred miles up, going nowhere new. Breaking out of low Earth orbit again represents not just a technical achievement, but a psychological and cultural shift. It says we're ready to move beyond incremental progress and attempt something genuinely ambitious. It reconnects us with the bold vision that Apollo represented, updated for our modern era with more sustainable approaches and broader participation. Whether we succeed or stumble, the attempt itself matters, demonstrating commitment to exploration and discovery. The role of artificial intelligence in future lunar missions will be substantial. AI can help autonomous landers navigate safely to the surface, assist rovers in identifying interesting geological features, optimize resource extraction, monitor systems for anomalies, and even provide companionship for isolated astronauts. Machine learning algorithms trained on vast datasets can spot patterns humans might miss, accelerating scientific discovery. As AI capabilities advance, the line between robotic and human missions may blur, with AI serving as a force multiplier for human explorers. Quantum technologies represent another frontier that might impact lunar exploration. Quantum sensors could provide unprecedented precision for navigation, gravity mapping, or detecting resources. Quantum communication might eventually offer secure, unhackable links between Earth and the Moon. Quantum computing could help solve complex optimization problems in mission planning or scientific analysis. These technologies are still developing, but they illustrate how emerging capabilities might transform space exploration in ways we're just beginning to imagine. The intersection of space exploration and environmentalism will likely intensify. As climate change accelerates and Earth's environment degrades, some see space as an escape hatch, others as a distraction from urgent problems. The reality is probably more nuanced. Space technologies help us monitor and understand Earth's climate. The perspective from space fosters appreciation for our planet's uniqueness and fragility, and developing sustainable living systems for space habitats teaches lessons applicable to Earth. These aren't competing priorities but complementary approaches to ensuring humanity's long-term flourishing. Private space stations are being developed to eventually replace the International Space Station when it's retired later this decade. These commercial platforms will support research, manufacturing, and tourism in low Earth orbit. They represent infrastructure that could support lunar missions, serving as assembly points or testing grounds for technologies. The ecosystem of space infrastructure grows richer and more complex, creating capabilities that make lunar exploration more feasible and routine. Asteroid mining remains speculative but potentially transformative. Many near-Earth asteroids contain water, metals, and other resources that could supply lunar bases or be used for construction in space. If economically viable extraction can be developed, it might reduce the need to launch materials from Earth's deep gravity well. This could dramatically change the economics of space activities, but we're far from proving these concepts, and many technical and economic hurdles remain. The development of nuclear propulsion systems could revolutionize space travel. Nuclear thermal or nuclear electric propulsion could cut travel times to Mars in half or enable missions to the outer solar system that would be impractical with chemical rockets. For lunar missions, nuclear systems might be less critical, but for the broader vision of exploring the solar system, they're increasingly seen as essential. NASA and the Department of Energy are developing these technologies. Though actual flight demonstrations remain years away, space tourism, while not directly related to lunar exploration, changes the space economy in ways that support exploration. As more people pay to experience space, launch costs decline, infrastructure improves, and public interest increases. Companies like SpaceX, Blue Origin, and others see tourism as a market that can fund development of larger capabilities. Eventually, wealthy tourists might visit the Moon, creating a revenue stream that supports the infrastructure enabling scientific missions. This commercialization represents a fundamental shift from Apollo's government-only approach. Looking ahead 20 or 30 years, if current plans succeed, we might see a thriving lunar economy with multiple national bases, commercial mining operations, scientific research stations, and even tourists visiting for brief stays. Dozens or hundreds of people might live and work on the Moon at any given time. Propellant manufactured from lunar water could fuel spacecraft heading to Mars or beyond. Astronomical observatories on the lunar far side could peer deeper into the universe than ever before. This vision seems ambitious, perhaps even unlikely, but it's what current programs aim toward. Alternatively, we might see another false start. Lunar missions flown a few times before being cancelled due to budget pressures, political changes, or technical failures. We could end up circling in low Earth orbit for another 50 years, accomplishing incremental progress, but never quite breaking out to sustained exploration beyond. History doesn't guarantee progress, and the path forward isn't predetermined. Success requires sustained commitment, adequate funding, technical excellence, and probably some luck. What makes Lunar return harder than Apollo? It's the accumulated complexity of everything discussed in these pages. Higher safety standards, environmental regulations, international coordination, commercial partnerships, more ambitious objectives, tighter budgets relative to goals, risk-averse culture, more complex technologies, legal uncertainties, competing priorities, all these factors interweave, each adding friction and difficulty. Apollo had the advantage of simplicity born from urgency and single-minded focus. Modern programs sacrifice that simplicity for sustainability, inclusivity, and broader benefits. Yet this complexity also represents progress. We're trying to do things right, to build foundations for lasting presence rather than achieve one-off stunts. We're including diverse voices and perspectives. We're developing commercial capabilities that could make space access routine. We're thinking about environmental protection, international cooperation, and long-term sustainability. These are features, not bugs, even though they make the endeavor more challenging. The question isn't whether returning to the moon is harder than Apollo. It clearly is in most respects. The question is whether the harder path is worth taking. If we can establish sustained lunar presence, develop the technologies and experience for living off Earth, inspire new generations, expand scientific knowledge, and perhaps lay foundations for eventual Mars missions, then the difficulty seems justified. If programs get cancelled after enormous expense with little to show, future generations will wonder why we didn't choose simpler, more focused approaches. Only time will tell which scenario unfolds. The next few years are critical. Artemis 2 and 3 will demonstrate whether the systems NASA and its partners are developing actually work for human lunar missions. Chinese missions will show what their capabilities and ambitions truly are. Commercial lunar landers will prove whether private companies can operate reliably on the moon. Countless technical, political, and economic factors will determine whether this time we stay. The moon waits, patient and unchanging, as it has for billions of years. It doesn't care whether humans return or not, but we should care. Not because the moon itself is the ultimate destination, but because reaching it again represents a test of our capabilities, our commitment, and our vision for humanity's future. The difficulty of that test doesn't diminish its importance. If anything, the challenges make success more meaningful, demonstrating that we can accomplish extraordinary things even when they're hard, even when simpler paths exist, because we believe the destination is worth the journey. Speaking of space journey, check out the video on the screen if you want to know why anyone who goes to Mars will never come back to Earth. The real science shows that traveling to Mars isn't just about getting there, it's about the irreversible changes to your body, mind, and life. It's a must-watch.